Alrighty then, this is the example from the Kaltura slideshow about older and younger people. In this example, a social scientist wants to compare the working hours of a group of younger people and a group of older people. We know that the younger people have a sample mean of 52.9 hours of work per week. The sums of squares for the sample of younger people is 23, and there are 20 of those folks. So I'm using the subscript Y for younger. For the older folks, the sample mean is 48.2. The sums of squares is 24, and the N for the older folks is 30. Alpha was 0.05 for this problem. Alright, so where do we start? As always, with the hypotheses. The null hypothesis, well, here we have two samples of groups of people, one younger, one older, theoretically representing two different populations. When we think about the population mean for younger, we think about the population mean for older. According to the null hypothesis, there should be no difference between those two, right? Those two populations from which these samples are theoretically drawn does not differ. The alternative hypothesis, well, we still have the population mean for younger and the population mean for older, but this researcher wants to see if the younger people work more. If that is true, then the population mean for younger will be greater than the population mean for older. Working more means a higher population mean, so that will have a greater than there. The second step, I'm going to put the second step up here this time. The second step of hypothesis testing is the rejection region. And in this case, it's a t-test. We know it's a t-test because nowhere is there a population standard deviation. We can think about, even though we don't know these population means, we can still reason about them as to whether if they're not different or if one is greater than the other. Right? We don't need their exact values to think about them logically. But to do the mathematics, we do need to know sigma, the population standard deviation. Since that is unknown, makes this a t-test. So I know I'm going to do a t-distribution. T-distributions have 0 in the middle. The three things I need to know for rejection region for t is where it's going to be. The greater than puts it over here. There's the first thing. I know where it is. I know it's going to be alpha 0.05 because the problem said use alpha 0.05. And then we need the degrees of freedom, which here is n plus n minus 2. 20 plus 30 minus 2 is 50 minus 2, which is 48. Now I know the table does not have 48 degrees of freedom in it, so I invoke the Price is Right rule, and the Price is Right rule is I go as close as I can without going over. So we use effectively, right, the degrees of freedom 40, and that critical value is 1.684. So we're going to reject the null hypothesis if the t that we obtained, t obtained, is greater than or equal to positive 1.684. All right, so there's the first two steps. Now the mathematics in the third is a little bit more complicated and drawn out. So what I'm going to do is erase these hypotheses to give myself some more room. I'm going to save the numbers for now. But remember the t formula is x bar 1 minus x bar 2 over the standard error. Now theoretically there's a difference between the population means here, but that's always going to be 0 for us, so that effectively drops out. So to do this, what do I need? Well, we need the two population means. Got them. They're given. I need to find the standard error. Right? This is where the chain comes out. Right? To find the standard error, I need to find the pooled variance. So let's start with that. Pooled variance is s squared variance subscript p for pooled. And pooled just means that it looks at the variability of the two samples together and kind of averages them together. When we did a single sample t-test, we just used the standard deviation for that single sample. Now we've got two samples, so we've got to combine them, and we do that effectively by pooling or averaging them. So the formula for the pooled variance is the sums of squares of one plus the sums of squares of the other divided by n plus n minus 2. Well, that's the degrees of freedom. I just figured that. Right? Degrees of freedom is 48. I'm going to use 48, right? Not 40. 40 was just for the table. Price is Right rules just for the table. Right? I know n plus n minus 2 is 48. That's what we're going to use. Sums of squares 1 is, what do we got? 23 for younger. Sums of squares 2 for older is 24. So I get 23 plus 24 over 48 is 47 over 48, which gives me a pooled variance of 0.98. All right, there's my pooled variance. I'm going to write that. I'm going to put that right here. Pooled variance equals 0.98. I want to keep track of that because to find the standard error, I need the pooled variance. Pooled variance over n for the first plus the pooled variance over n for the second sample, and I take the square root of the whole thing. Right? Well, the pooled variance is 0.98, and it's the same thing. It's weird. It gets used twice. That's okay. 0.98, 0.98. And then I have the n's. The n for the first sample is 20, n for the second sample is 30. I don't want to remember to take the square root. So this is 0.98 over 20 plus 0.98 over 30. 0.98 divided by 20 is 0.05. To that we add 0.98 divided by 30, which is 0.03. I get the square root. Add those together, right? I get the square root of 0.08. We take that square root and we get a standard error of 0.28. That's the denominator of the t-test, right? 0.28, 0.28 goes right here. So, there's the standard error, right? To do the t-test, I need the pooled variance. Using the pooled variance, I can find the standard error. Once we have the standard error, we can find the t-value. So now I just need to look at the difference between the sample means. Now, according to the null hypothesis, right, this is 0. According to the alternative hypothesis, I should see a positive number. Let's see what happens. Y first. Always want to follow the order of the hypotheses. So the first sample is 52.9 for younger minus 48.2 for the older. Gives me a difference of 4.7 hours. Right, 4.7. That tells me the younger people worked 4.7 hours more than the older people. 4.7 then divided by 0.28 gives me a t obtained of 16.79. Right, so now we go to the fourth step. All that was just the third step. The fourth step is making a decision, and in this case we can see the t obtained is indeed in the rejection region. 16.79 does exceed 1.684. So the decision is to reject the null hypothesis. We have evidence. We have evidence that the young people, right? Young people just work more hours than the older. Right? We have evidence they work significantly more hours than the older people. Right? We know there's a difference. 52.9 is different from 48.2. But we do the hypothesis testing to see if it's a significant difference. Significant difference means it's one that's in the rejection region. Means it's one that would occur due to chance, less than 0.05. right? Less than 5 times in 100. Assuming the null hypothesis, it's a rare outcome. So significant differences are special differences. They're rare outcomes. They're not due to chance alone. That tells me there's a meaningful difference between the populations. The population of older folks does not completely overlap the population of younger people when it comes to working. Now, the possible error we could have made here, because we rejected this, could be a possible type 1 error. Right? Type 1 error is a false alarm. It could be that the data is telling us one thing when the reality is something different. Here the data is telling us there's a significant difference. But the reality might be that there is no significant difference, that there truly is no difference between the work hours of these two populations. The only way we'll know if it is indeed a type 1 hypothesis is by replication. Other people doing the same study, the same analysis, with different groups of people, perhaps slightly different dependent variables, but only time will tell if this is truly a correct finding or a type 1 error.